Hello everyone. In this video we are going to look at a particle's kinetic problem using the cylindrical coordinates, or the 2D version of that, which is called the polar coordinates. So here we have this bar which is rotating in the vertical plane, and it starts rotating with a constant alpha of 1 radians per second squared from rest, where the angle is 0 degrees, and there is a mass of 2 kilograms on it at a distance, radial distance of 1 meter from the origin, which can stay at 1 meter from origin as the angle is increasing from 0 degrees until it goes to 30 degrees. When you get to 30 degrees, now this mass starts to radially move. Right? So it's not going to be static friction anymore, it's going to be kinetic after 30 degrees. So you want to find mu s in this problem, and also say that when it starts to radially move, which direction does it go? Is it going to get closer to the origin or further away? So here we are going to draw the free body diagram of this 2 kilogram mass, but when the bar has rotated. So we assume that here this bar is going to rotate an arbitrary angle theta, and this mass is on it. So in this situation, I'm going to draw the free body diagram of the block, okay, for arbitrary angle theta. So this is my block, and the forces on it are mg, as well as the normal force N, and a friction. Okay, now as long as it has not moved yet, right, you might wonder which direction is going to be the friction. So you might say, well, if this is on an inclined surface like this, on a wedge right that, then it wants to move down, so the friction has to be tangent to the surface upward. Is that right? We're going to find out. But it has to be either radially outward or inward, okay, depending on which direction it wants to go. So this is my FVD. The unit vectors I have is ER in the radial direction outward, and E theta in the direction of increase in the angle. EZ is out of the board, perpendicular to the board toward us, but we don't need it in this problem because it is a 2D problem. So we just use the polar coordinates that we have. So this is my coordinate frame, this is my FBD, and now it is time to go ahead and write the governing equations. So I have two axes, therefore I have two governing equations. Some forces in the radial direction. It is going to be equal to F minus mg sine of theta, where this angle here is theta. And this is equal to m times a radial. And if you know from your kinematics, the radial acceleration is r double dot minus r times theta dot squared. And then we have some forces in the theta direction, which in this case it is going to be n minus mg cosine theta. That is equal to ma theta. And the theta acceleration is r theta double dot, or alpha basically, plus the Coriolis term, 2r dot theta dot. So these are my governing equations 1 and 2. Now with these, let's see if we can solve the problem for part A, which is asking for mu s. Okay, so when the angle is 30 degrees, or just marginally less than 30 degrees, the object has not slided yet. So it has kept the radial distance of r equal 1. Okay, so if we solve for these equations when theta is equal to 30 degrees and r is equal to 1 meters and it is constant, which means if you take time derivatives, r dot is going to be 0 and r double dot is going to be 0. Okay, so there is no radial motion before you get to 30 degrees. Therefore, if you look at these equations, I have r double dot as 0, I have r dot as 0, I have r as 1 meter, I have the mass 2 kilogram, I have angle at 30 degrees, I don't know n. When it is basically about to slide at 30 degrees, it's on the basically edge of sliding, this F has to be maximum static friction. Clearly this is a static friction when it has not slided yet, and of course at 30 degrees it is doing the best it can to keep the object in place, so it is generating the maximum static friction. So Fs is going to be mu s times n. So it's not just another unknown. The question is, how much is theta dot, how much is theta double dot? Theta double dot is given as constant 1. So this number is given 1 counterclockwise. Good. But we also need theta dot. So here, since theta double dot is constant, right, at 1 radians per second squared, you know when the angular acceleration is constant, the angular velocity is going to linearly change with time, but here we don't know what time it takes to go from 0 to 30 degrees. We just know the initial angle 0, the final angle 30. We know initially theta dot was 0. Finally theta dot at 30 degrees we don't know. And we know the theta double dot. So whenever time is not involved like this, I would use my time independent formulas, right? Since theta double dot is constant, that means I can write that theta final squared minus theta initial squared is equal to 2 times a, which in this case a is alpha, or angular acceleration, times delta theta, correct? So this is the time independent formula that we have, or omega 2 squared minus omega 1 squared is 2 alpha times delta theta. That's the formula we have for angular motion when alpha is constant. So initially we are starting at rest. Finally we need to find it. Theta double dot is 1 and delta theta is 30 degrees. But remember this formula for it, delta theta has to be in radians. So that 30 degrees, you have to multiply it by pi and divide it by 180, right? Pi over 6. Therefore, if you solve here for theta 2 dot, which is the number that you are going to use in that formula, it is going to be the square root of 2 times 1 times pi over 6, right? So it's going to be square root of pi over 3, basically, which if you use MATLAB and calculate it, we will get 1.02 radians per second. Okay, so now I have my theta dot term as well. This is 1.02. And as I said, r is 1. So if I look at my equations 1 and 2, right, they can give me a bunch of info. If I look at equation 2, the only unknown in equation 2 is clearly n, right? Because everything else is known. So here I will solve for n. N is going to be 2r theta double dot, which is just 2, and then plus mg cosine of 30 degrees, correct? So if you calculate it, you will get 18.99 Newton. That is the normal force from the bar onto the block, right? And now, if I go ahead and plug it into this top equation, where mu s is unknown, then I can solve for mu s because everything else is known except for mu s. So here we solve for mu s. Every term again is known here. So if we solve for mu s, the answer will be mu s equal to, with 2 decimals, 0.41. And you know it's unitless. So that is the answer. Mu s is 0.41 for this motion to happen. Now, if I want to answer part 2, where it is asking me whether the block is going to slide down or slide up or away from the origin, it's better to look at this problem a little bit with parameters and without numbers, right? At least for f, if we replace it with mu sn, and n we find it from the bottom equation, which was mg cosine theta plus mr theta double dot. So if I go from equation 1 and 2 together, right, if I combine equation 1 and 2, you'll see that you will get f minus, and f is itself mu s times n, so I can replace it right here. It is mu s times n, and n from equation 2, if you solve for it, it is going to be m times g cosine theta plus r theta double dot, right? That is n. So mu s times n minus mg sine theta, correct? This is equal to m times r double dot minus r theta dot squared. Now I can cancel the m's from both sides. And now the thing is this. If you look at these terms involved, one of them is g cosine theta mu s, the other one is mu s r theta double dot, and the other one is negative g sine theta. If you look at their magnitudes in this problem, mu s is 0.41, g is 9.81, cosine of theta is, let's keep it as is, cosine theta, plus r is 1, theta double dot is 1, correct? And then minus g times sine theta equals r double dot minus r, which is 1 times theta dot squared, right? So now if we look at these numbers, so as long as theta is up to 30 degrees, the what's going to be the sine of the left, or if you want, we can even take this r theta dot squared to the left hand side. So say this is plus r theta dot squared, right? And this way you calculate your r double dots. Right? So this is going to be your r double dot as function of theta, theta dot, and so on in general, before you get to 30 degrees. Once you pass 30 degrees, right, and your r also starts to change, then you will have the r dot term as well. But let's say so far r has not changed, there is no r dot, r is 1. So if r wants to start changing, first r double dot should be non-zero. When r double dot gets non-zero, it means r dot is going to change from whatever it is right now, which is 0, to some non-zero value. And when you get a non-zero r dot, then r is going to change, correct? So for r to change, you need a non-zero r dot. For r dot to change, you need a non-zero r double dot. So you need to focus on r double dots and see how the radial velocity is going to change. So what you need is to focus on this equation and see what happens when the angle is increasing. So when theta goes bigger than 30 degrees, what's going to happen? You know that the sine function is increasing with angle as angle goes from 0 to 90 degrees. So sine of theta is going to be bigger than sine of 30. And cosine is a decreasing function from 0 to 90 degrees. So cosine theta is going to be less than cosine of 30 degrees. So this term is going to go down, while this term is going to go up. So what's going to happen if we temporarily focus on, let's say, just 1 degree more than 30 degrees, or a fraction of a degree more than 30 degrees? So theta dot has not changed dramatically. It's almost at the same number we found, 1.02. So because the positive part is going down, the negative part is going up. When at 30 degrees this whole thing was 0, now this guy is going to go what? Is going to go down, which means our double dot is, since it was 0, now it becomes negative. And negative means since our dot was 0, now our dot is going to change to negative numbers. And when our dot is negative, it means your radial distance is going to shrink. So your block starts to what? Go down, and that completely matches the direction of friction that we have over here. Now you might say, well, did the direction of friction that we used for when theta was between 0 to 30 degrees, was that also correct? Because as we just saw, the direction of friction when theta is bigger than 30 definitely should be upward, because the motion is going to be downward. But that's kinetic friction. What about the static friction? When theta was between 0 to 30, we just assume it's upward. Is that correct? The answer is yes. And why is that? Because if you look at the beginning of the motion, when you just start to move from 0 degrees, your theta double dot is 1. And if you look at this equation here, the time-independent equation, well, when delta theta is small, so the rod has not traveled or swept a long angle, delta theta is still small, a fraction of a degree, 1 degree or so, then your theta dot is going to be a very small term, right? Your theta dot is going to be a small term, or omega. And so the centripetal acceleration that you have, this guy, is going to be really small, because your theta dot is still small. You have not achieved such a large theta dot, right, or omega. You see, even after 30 degrees, your omega is just 1 radians per second. So when this theta is just what? 1 degree, so this is pi over 180, your theta dot is going to be a very small number, and when you square it, it's going to be even smaller. So your centripetal term is small, therefore you don't need a ton of force to keep this guy basically rotating along the circle in the beginning, because your theta dot is not big. And so the total force that you have in the r direction, negative r direction, does not need to be so big. Fine. So now what's going to happen? When you have the block on it, it doesn't have too much of centripetal acceleration, right? And you know clearly your mg sine theta is going to be providing that acceleration, and theta is small, so mg theta is not going to be big as well, but that's enough to give it that small centripetal acceleration. So definitely you do not need friction to come to the help of mg, right? And tries to add a radial component. So instead of this being like that, it becomes negative fs. So now both of them are helping for this negative radial term. You don't need that because your centripetal term is not large. Or for the people who use the term centrifugal force, which is not really an actual force, it's just an imaginary force. The centrifugal force, if you use that, which I'm against it, but if you use that as an extra force, that force is not large enough now to move it radially out. So you need the friction to be radially in. So the motion is completely dominated by mg, right? By mg sine theta. And that term is radially inward. So the motion has to be radially in. It's an inclined surface, basically, like this, with a small angle. And you know, definitely under the weight, the block starts to slide down. When that mr omega square term becomes really large, and again, if you consider it a force, which we should not, that force which is radially out can dominate mg sine theta, and now the object can slide moving in that direction, so the friction is backwards, right? But especially in the beginning of the motion, and by the time that the omega is not really super large, the sliding is always going to be inward, so the friction has to be outward like this. So that assumption we made in the beginning of the problem is absolutely right. And you see clearly we could solve the problem. We could predict the direction of motion after 30 degrees, and I guess we can explain everything. Thank you so much for your attention. I'll see you in the next example.